Yeah. Lorenzo Magrini will be giving the seminar. Lorenzo comes from far away because he flew all the way from Europe, braving not just the pandemic, but all the regulations, the changing regulations and more or less reasonable requirements for actually traveling long distance. So Lorenzo was an undergraduate at the University of Rome, where he studied for his undergraduate degree quantum optics, and then he has been PhD student in Vienna in the group of Markus Aspermeyer, working on various aspects of optomechanics using very small objects. So there's some similarity to some of the stuff my group does, but they work on smaller things. And so he's going to be telling us about at least one of the experiments he's participated while a graduate student there. Thank you.
Thank you, Giorgio, for introduction. Thank you for having me. Thank you for coming. So yeah, I will talk about the biggest project I've been working on during my PhD in Vienna, quantum measurements and control of mechanical motion at room temperature. Now, the mechanical motion we are going to study, or we have studied, is the motion of a levitated dielectric sphere made of glass, about 100 nanometers in size, which is levitated in a focused laser beam, an optical tweezer. And the goal of the experiment was to try and measure the displacement of this particle at the quantum level and try to see if this particle behaves like a quantum harmonic oscillator or not. So the main motivation for research in the Aspermeyer group is trying to control these harmonic oscillators of increasingly growing size. Hopefully one day when we'll have a quantum harmonic oscillator of a size that is large enough that also gravity is measurable on the same object. Try and see interesting stuff there. And so we have a different set of experiments. Some experiments, which is the kind of experiments I've been working on, levitating very, very small dielectric particles, about pentagram masses, and trying to observe quantum effects on these. And very small, but still relatively large for a quantum system. And the top-down approach is to try and measure gravity on very large objects that's very small for gravity. And we have experiments, latest experiment in which we have measured the gravitational pull of a millimeter-sized gold sphere. And then the last class of experiments we have is something in between, hopefully the system in which both gravity and quantum effects will be observable, which is using superconducting levitated spheres of about few hundred microns of size. So the reason to do optical levitation with dielectric particles, it's not only for testing quantum physics at its limits, it's also used there are also very good sensors when they are used for thermodynamics experiments in equilibrium, out of equilibrium, in the quantum regime, in the classical regime. They're used, we had an experiment in fluid dynamics these particles were trapped in hollow core fibers, and just measuring pressure gradients is very easy there, while simulating fluid dynamics in microfluidic channels is a problem that is really not easy. So an experiment that took 2 microseconds required a simulation of a month on a very big computer. And of course, for dark matter detection, they are one of the latest experiments that are digging a bit of the parameter space lately in Yale and also here. So my talk today will be about first how we manage to control in real time the quantum trajectory of this levitating particle by measurement and control. And in a second part, a bit shorter, I will show how we were also able to observe, to generate and observe under motif squeezing at room temperature without a cavity. So the fundamentals of the experiment is really, really simple. We have a particle that is trapped in an optical tweezer, and classical forces define a harmonic, a potential that we can approximate to be harmonic, and in which the particle oscillates at about 100 kilohertz. And now, as the particle is oscillating in this optical field, it scatters light, and if we measure the phase of the light that is scattered, we can infer the position of the particle in real time. As if it's displaced, the light is delayed depending on the displacement of the particle. Now, this is all classical effects, but light is also a quantum field, and every photon that scatters off the particle introduces a recoil onto the motion of the particle, disturbing its motion. As well as the discreteness of photons introduces a recoil on the particle motion, Bostonian statistics also defines a shot noise additional to the measurement we are performing on the position of the particle. So quantum fluctuations define a back action on the particle and an imprecision on the measurement. And these are linked by the Heisenberg uncertainty principle. In addition, we also may have some residual gas, which adds disturbance without contributing to our measurement, which is bad. We have to get rid of those. So if we take the Fourier transform of the signal that is measured, we can look at the spectrum of the displacement of our mechanical oscillator, and we can analyze the different contributions to it. And well, the fundamental contribution, the one we actually want to observe in this experiment, is the quantum motion of the harmonic oscillator. The particle, if it's a quantum harmonic oscillator, it will have a 0-point energy to which we can associate the 0-point motion. This we cannot get rid of even at 0 temperature. And then there is the force noise that is introduced by the photons that are scattering off the particle. It's transduced to a displacement noise through the mechanical susceptibility. And this is the back action peak on top of this. And then we have the imprecision noise, which is the white shot noise that is given by the statistics of light hitting the detector. Again, back action and imprecisions are limited by H bar and the Heisenberg uncertainty principle. Now, in real experiments, we have, as I said, also gas molecules hitting the particle. These introduce an extra force noise, which lifts the total peak of the measured spectrum. And we also have inefficient detection. It's impossible to detect all of the photons, and this lifts the flat background of our measurement noise. So together, these two effects contribute to hiding the dark blue quantum motion of the harmonic oscillator, and we have to minimize these effects in order to observe this. So we can now redefine a total force noise and an effective imprecision noise, and see how the Heisenberg uncertainty relation is is degraded by these effects. Okay, so a quantum measurement needs to be strong in the sense that we have to have much bigger back action than thermal force noise contribution, and it has to be efficient in order to achieve the quantum level, which arbitrarily we define if we can observe the amount of displacement that is introduced by an occupation of the photon of the mechanical oscillator of one. So cooperativity is usually defined as the rate of the noise introduced by the back action force and the thermal fluctuations, or equivalently the ratio of the decoherences introduced by the two effects. And these are proportional to the photon rate, so the amount of photons hitting the particle, measuring it, but also disturbing it over the decoherence rate introduced by gas collisions and some geometric factors. And so usually we copy a lot from the AMO community, and cavities are the way to go in order to enhance cooperativity in a measurement. And this is what we did. This is what we did in 2018, trying to couple a particle to a photonic crystal cavity. We improved a lot efficiency, almost to the limit that is required, but we couldn't go to very low pressures, and this destroyed the cooperativity, actually. So in a second experiment, which is the one I will talk about, we actually used confocal microscopy in order to efficiently detect the particle, and we went to very low pressures, and we were able to control the particle into the quantum ground state. So this is the first experiment I will talk about. Now, again, we go up in cooperativity by increasing the vacuum level. So we have no particles left, no gas particles left. They're barely disturbing the motion of the harmonic oscillator. How do we increase the efficiency of the measurement? Which up until I started my PhD was 3 orders of magnitude lower than what was required. So first thing is we look at how this particle trapped in the tweezer is scattering photons. This is the dipole emission of the particle. As I turn polarization, you see this donut-shaped scattering of a dielectric subwavelength object, and so light is scattered perpendicular to the polarization of light, and that's where we want to collect the most. Of course, it's not really possible to collect all of the photons because they go everywhere, and one would need a huge detector, weirdly shaped. But there are ways we can optimize the detection. And historically, people have been detecting the light scattered by the particle in forward detection, which introduces an issue that is well known by microscopists, at least, by bright field. In bright field microscopy, that the light that is trapping the particle is hitting the detector together with the light that is scattered by the particle. And this introduces huge backgrounds without helping the efficiency of the measurement. So what we did is we put the detector in backscattering, as we also have here in Greta's group. And now we can only detect the light that is scattered by the particle without any background. And because there are some stray reflections from the surfaces trapping or controlling the optics, the lens and wave place and everything, we also introduce confocal spatial selection of the light that is scattered by the particle. We spatially select with a single mode fiber rather than a pinhole, but that's basically the same. And And now there is also another reason why one wants to detect in backscattering rather than forward scattering. This is that the phase delay that is introduced by the particle onto the light is almost a constant in forward scattering. The particle will delay the light because it's a dielectric and it has a different index of refraction, but it doesn't really matter where the particle is. While for light that is reflected, it is strongly dependent on the position of the reflection. And the same goes for the back action. Photons that go in the same direction as they were coming, they have no momentum change, while photons that are reflected, they change the momentum by its decay vector. So defining this kind of setup, we managed to achieve an overall efficiency of 34%, which brings us at about 1.7 times away from the Heisenberg imprecision back action limit. And this is good enough to control the particle at the quantum limit. Now, this is an example of the spectrum we measure of our harmonic oscillator. We have, it's a weird scale, but you know, people usually do it like this in trying to show the standard quantum limit. So we have frequencies in log scale on the bottom, and the very, very left is on resonance. And we can really characterize as expected, the contributions given by imprecision noise, so the flat background, the quantum fluctuations, and the back action force noise. And we see that at about 20 kilohertz of resonance, we're only about 2 times away from the standard quantum limit, which defines the best sensitivity one can have with coherent light. So what is happening to the particle while it's measured? The particle is called an open quantum system that is continuously measured by weak measurement interaction. And in phase space, this is going around as a harmonic oscillator driven by noise would. And because it's driven by Gaussian noise, and it's a linear model, the state of the particle at each instant is only defined by the first and second moment. It's a Gaussian state. So the only 2 things we need to describe the state is the expectation values of position and momentum, and the covariances of position and momentum. So we have our state. It's continuously driven by scattered photons, and we have an outcome of the measurement, upon which we can condition our knowledge about the state. So we measure and we can infer what is the expectation value and what is the covariance of the state. Now, what is interesting and at first to me very surprising is that for a Gaussian system, for a linear Gaussian system, the dynamical equations that describe the evolution of the expectation values and the covariances are completely equivalent to a classical Kalman filter. So knowing the output of the measurement, we can feed this output to a classical transfer function, a filter, a very classical filter. And this will give us in real time the expectation values of the position, momentum, and covariance of the state, from which we can infer the quantum state. This means we can track in real time what is called the quantum trajectory of our harmonic oscillator. Now, in this, so the Kalman filter is so classical that was used the first time it was developed to go to the moon with the Apollo mission. So it's this level of classicality, let's say, and simplicity in the computation. And the way one does it is you define your system, your state space system, so position and momentum. You have a model of the system, in our case, a harmonic oscillator, maybe an input force that you want to apply some feedback, and the process noise, which is what drives the motion of the particle. In our case, it's mostly given by the photons that are scattering, the back action force noise. And then you define a detection model. So our output will be proportional to the position with some measurement noise. And the only difference with the classical system here is that measurement noise and process noise are again bounded by the Heisenberg uncertainty relation. And then one defines the observer or the Kalman filter, which is again the Langevin equation in matrix form. But rather than having the noise at the end of the equation, we have a correction which is given by the output of our measurement and the prediction of what is the state given the previous estimation we had. And this L factor called the Kalman gain depends on the ratios between the noise in the measurement and the noise disturbing the particle motion. And again, also the covariances, they are limited by the Heisenberg uncertainty relation. So let's have a look at the entire setup. How does it look like? This is the particle trapped in a vacuum chamber. We try to get rid of most gas molecules. Particle is oscillating at 100 kilohertz, trapped at 10⁻⁸ millibar. And the particle, we're lucky enough, it has, or at least for now, eventually one will want to get rid of them, but not in this experiment, has some charges, some extra electrons or too little electrons, but has a net charge. This is very useful in our case because we can place a couple of electrodes around it, and we can apply, by applying a voltage to these electrodes, we can apply linear force to the position of the particle, for which we can, I don't know, push it around, drive it how we want, cool it, heat it. We set up our confocal microscope with high efficiency, and then we perform homodyne detection to measure the scattered phase of the light that is coming out. And we feed this measurement of phase to our Kalman filter and reconstruct the quantum trajectory of the particle itself. And now, together with the Kalman filter, we can add a linear quadratic regulator, which is just an optimal controller that takes the state as an input and defines the optimal force that we should apply to the particle in order to minimize the variance of its motion. And we feed this to our electrodes, and we can reduce the motion of the particle in phase space. Now there is one last ingredient we need in order to claim we have a quantum harmonic oscillator, because in principle this all relies on accurate calibration of our system, and a small factor may ruin everything. So we add Raman scattering thermometry, which means so our harmonic oscillator is principle highly populated, up to 10 to the 8 phonons. And whenever light is scattered by the particle, most of it is scattered elastically and comes back with the same energy. But a small fraction is scattered inelastically, which means it has exchanged energy with the harmonic oscillator. And it may gain energy by absorption of a phonon from the harmonic oscillator, or the light may lose energy by giving it to the harmonic oscillator, increasing its occupation. So if we look, and if the oscillator is highly populated, the probability of gaining or losing energy is the same. But if the harmonic oscillator is for quite some time into the ground state, it cannot give any more energy to light. And so we will see a lower rate of photons that have gained energy. So photons coming out with higher energy are less probable than photons coming out with less energy, because we can always give energy to the particle, but we cannot always take energy from the particle if the particle is at its ground state. And this is how, by looking at the asymmetry of the sidebands, of the red and blue sidebands, we can estimate the actual occupation of the motion degree of freedom of our particle. And so we add this by using heterodyne detection. We don't want to lose too much light because we need efficiency in our controller on our Kalman filter, but we take up 5% of the light, feed it to a heterodyne interferometer, and we measure the asymmetry of the sidebands from which we can calibrate in absolute terms, in units of h bar omega, the energy of the harmonic oscillator. And it works. So this is data of trajectory of our harmonic oscillator in phase space, the output of our Kalman filter at an occupation of 2.8. And if we even add more cooling effort, this is another trajectory of our particle at occupation of 0.7. And you can see in the gray shaded area is the size of the covariance of our state. So we know the expectation value of our particle, and we know the covariance of the state. So this is a state that is always that small, turning around, driven by the measurement. And the best we can do is reduce the size of our state to the area of the gray shaded covariance we have. We verified this by sideband asymmetry, and it's always consistent with our measurements. And if we plot everything into a gain-dependent plot, so the x-axis define our effort in cooling the particle, so how much power we feed to the electrodes to reduce the amplitude of the motion of our mechanical oscillator. And both the Kalman estimation and the sideband asymmetry agree very well with the expected theoretical values that we predicted defined our model. Okay, so good. We have a nice harmonic oscillator in the ground state. And yeah, the smallest occupation we achieve is about 0.5. This is actually limited by the speed of our controller. There is a bit of a delay in the FPGA, which does not allow us to go over a cooling of 200 kilohertz. In principle, we should, if we had a perfect controller, we should be able to reach this gray shaded area at about 0.3, but yeah, but we can't. And this is not only, you know, useful because it's a ground state particle. It's also a very, very good sensor. So here we see that the detection efficiency allows us to discriminate, for example, a disturbance to the particle that is of the size of the momentum of 7 times the zero-point fluctuation. In this case, this is equivalent. So we think, still running statistics on this, but we think this is due to the impact of a very fast gas molecule on the particle. It's consistent, or the amount of hits we see and the impulse they give is consistent with what we expect at room temperature. And the Kalman filter is not only useful for let's say optimal control, it also allows, now here it's easy to see the effect of the impulse, but because we're cooling the motion very much, so the oscillations of the particles are very small. But in principle, we don't need to cool the particle in order to see the effect of this hit, because the Kalman filter allows us to do an analysis of the innovation sequence, and the only restriction is given by the size of the covariance of the conditional state we are measuring. So if we take the difference between the measurement and the estimated position, so here gray versus blue, independent of the occupation, we can always observe if the statistics of the noise we're measuring of the innovation, what is called the innovation sequence, is lying outside of the Gaussian distribution that is expected, and then detect in real time these hits, which in the perspective of dark matter detection measurements is probably more interesting. Now, of course, this particle is very, very small, so probably does not have a very good cross section for experiments of this type, but these considerations are independent of the size of the particle. Okay, now the second part, this is side result we had from this experiment, is observing thunder motif squeezing from the interaction of light and mechanics at room temperature and without a cavity. So whenever light hits the particle, it has fluctuations in its amplitude. Photons are follow again Poissonian statistics, and the amplitude fluctuations are transduced to the mechanical oscillator in the form of a force fluctuation. And this force fluctuation is transduced to position noise through the mechanical susceptibility, and position noise is then transduced to phase noise in our measurement output. And so if we start with a coherent state, which is limited in which amplitude and phase are uncorrelated, we have created, by the interaction with the harmonic oscillator, we have created the correlation between amplitude and phase. Now, the phase noise depends on the amplitude noise of the input field. And if one takes the Hamiltonian of our state, computes the equation of motion of the output field, and then defines a quadrature and looks at the spectrum of a particular quadrature, one sees that the contributions to the spectrum of arbitrary quadratures that we detect is given by the flat shot noise, as usual, the displacement noise of the particle on top of that, and a correlation term that arises from this called thunder motif squeezing correlation between amplitude and phase. So if we choose the right angle, the correlation term may be dominant or may be big enough to bring our total power spectral density below the level of 1. And typical spectra look like this if you choose the right angle. So yeah, so in that tiny little frequency space, the total noise is smaller than the noise that we expect from a coherent state, meaning we have a squeezed state of light. And yeah, if we scan the phase, so this is a spectrum, we have frequency on the vertical axis. And if we scan the phase, this is theoretical plot, we see that at pi half, we have the typical Lorentzian peak of the mechanical motion of the harmonic oscillator. At 0 degrees, both terms vanish and we just have shot noise, so just flat background. And at about 10 degrees, we have the best ratio between the green correlation term and the large red mechanical noise displacement. And right, so thunder motif squeezing is usually degraded by 2 factors. The first is losses in the detection channel. which lift our flat background noise. And the second is thermal noise. So gas molecules driving the motion of the particle, they lift the mechanical noise displacement. Well, the green correlation term always remains the same. So in order to fix these two problems, what one usually does is you place a cavity which amplifies the interaction with a mode that can be detected, so increases efficiency effectively, and also increases cooperativity. And also, if you put it into a cryostat, gas molecules are much slower and they disturb the motion of the particle less. And all of the experiments until now, so with atoms, with gigahertz nanostructures, and even with larger mechanical oscillators, small suspended mirrors, they always worked with a combination of either cavity or cryogenics or both. Now, in this experiment, we don't use either cavity or cryogenics, just because, I don't know, we show that it's possible to do even without. And the only difference with the setup I showed you before is that rather than having light in the heterodyne detection just 5%, we increase the efficiency of the heterodyne detection at the cost of losing cooling rate in our mechanical oscillator, but we don't care. That's not a factor that counts. And then we demodulate the output of our heterodyne to reconstruct simultaneously perpendicular quadratures of the output optical field. And because we can reconstruct at the same time both perpendicular quadratures, we can reconstruct the spectrum at all angles of our harmonic oscillator. And we see that we can squeeze light about 10%. It's not much. It's not particularly useful in noise reduction or, I don't know, LIGO application, for example. But it's a signature. And we can also reconstruct it at all phases because we have full tomography from our heterodyne detection. And this is our data, which very well resembles the expected terrestrial plot. And yeah, and that's it. So yeah, I hope I convinced you of our results in real-time optimal quantum control at room temperature, and the second von der Motiv squeezing at room temperature without the cavity. It was a bit shorter than
questions. I mean, you run.
No, you can.
I got a question.
Yeah.
So, in, great results. Thank you for setting them. What is the cooling limit for the feedback scheme percentage?
for this.
Like, is there an ultimate expectation value of n that you can hope to achieve? You had a great band on your plot.
Yeah.
I'm just wondering what sets the ultimate limit of that scheme.
So the gray band is defined by the total efficiency of our measurement. So I think we can improve by changing technical issues such as transmission of our microscope objective and efficiency of the detectors and the collection angle of the.
So there's not, like, let's assume all that stuff goes to Unity. You're living your dream. There still must be a fundamental limit with that method. With a classical controller,
I think if the dynamics is slow enough compared to the FPGA that is controlling the output, the limit is always basically 1 over the efficiency square root. So, but practically, there's no, I mean, except getting rid of the quantum fluctuations, those are always there. So, yeah. I mean, and n equals 0.1 plus 1/2 always. So that the 1/2 is always there.
Right. I was just thinking because you're essentially stochastically collapsing the coherent evolution of the object. That and that's how you get the information to the classical controller. That must have unavoidably that has noise.
It's so for the classical control.
Yeah, you're feeding a classical measurement into that controller. So at some point you're putting noise into the system. I would say you're collapsing a wave function.
Yes. So in principle, let's say the gray shaded area is achieved at the limit of infinity gain.
Okay.
Which is technically difficult because you would need infinite power in your controller. But yeah. So this is.
So I think of it as the measurement as being a weak measurement. Then it's when. Oh, all right. Thanks. I got the question answers.
I guess I have maybe a related question. So can this sort of classical feedback also be used to make non-Gaussian states, or what are sort of the prospects in making non-classical states?
So in non-Gaussian states, you cannot anymore say that the Kalman filter is reconstructing the quantum trajectory of the state. What you can do is you can use what they call an extended Kalman filter, which locally approximates the nonlinear dynamics that one would have to a linear model, knowing where you are in the total landscape, and that works. People have done experiments with photons and using optimal control to generate or to maximize entanglement. I think. Yeah, the only issue. So practically, I think optimal control is very useful. It helps. Conceptually, you cannot anymore claim your quantum trajectory is reconstructed by the filter itself, because the problem is not solvable.
So like, is there some requirement about like I need some nonlinearity in my measurement process, or I guess I'm just trying to understand, what it takes to go beyond making this Gaussian state, which is already very impressive, getting this ground state, but
to go beyond. I'm not really sure. Maybe, yeah.
sure, that's fine. Thanks. Yeah.
And actually, I was confused. I didn't notice it when I visited you guys, but you use this Raman spectroscopy to essentially measure the temperature, but that's the temperature of the center of mass of the particle. Why that's what you're measuring as opposed to the eternal real temperature, of the eternal degrees of freedom of the particle itself, which is not a single atom, so it's got some structure inside. I would have thought that the Raman spectroscopy would actually measure that temperature, not the temperature of the motion particle.
It depends at what frequency you're looking at. So our sidebands, we compare the height of the sidebands at the mechanical resonance. So the energy exchange is 100 kilohertz. It's due to that degree of freedom. Of course,
But can you also see in a different frequency the internal temperature of the particle itself?
we never tried. I guess that would be very, very high frequency.
Right.
But I guess.
Because that's the mystery on those things, right? There's always been, something.
Sure, I guess one would just need, gigahertz detector. Maybe then it's easier to do optically.
That's what I was thinking. It's like
The red camera.
Yeah.
Glowing red hot. How big is the particle? I may have missed that in the.
It's 70 nanometer radius.
And it's fused silica.
It's yeah, they call it fused silica. I think it's grown chemically some process.
So this is a Stoker process.
Yes, yeah.
Yeah, so there, I mean, I don't know, we should call it really fused silica because.
Yeah, they call it like that. I mean, when you order it, is
They call it fused
yeah,
silica.
but yeah, it's
But they don't have that because we measure the density, at least, well, we have larger particles, but we measure the density and it's quite a bit lower than the density of fused silica. Which presumably means they're it's like a sponge. I think of it as a sponge, but it's.
So we have a setup in which we have microscopic cavity, and by looking at the coupling of the linear coupling versus the quadratic coupling, you can actually infer the mass of the particle in absolute terms, and it's consistent with 1800 kilos per meter.
What manufacturer are your nanospheres from? Do you happen to know the
Microparticles.
Okay, yeah. But it's consistent with the number that we
Okay.
see for that manufacturer.
Yeah. So yeah.
Yeah, so this is kind of a crackpot question, but have you estimated the possible graviton emission rate from the motion of the particle on the track? Like how long to make a single graviton? Assuming that the graviton obeys like the standard Planck's constant.
No, I have no clue.
How would that scale with the oscillator's resonant frequencies if you have something that's like
Well, it scales with like, I mean, the more
So
it
it's longer.
accelerates, the more, yeah. So it's, I mean, once if you want to start studying both, you're testing quantum gravity, then that's an interesting thing to know.
Yeah.
That like an emission of a graviton is a wave function collapse event.
I don't know what you said, but that thing read you Mark saying a big rabbit. I got distracted because a big rabbit, how can it possibly
All the time. So good. So you it automatically translates around.
So Lorenzo, you said you're able to get the mass in absolute terms by comparing the quadratic and linear coupling in cavity. So that, as opposed to the usual where you get a ratio of m over t from like looking at some Brownian spectra, it's like the usual method that people use to infer masses. There's that one different by Ricci.
Well, I said absolute terms now. I think you still need to assume
It's thermalized with a gas or something like that.
no, that doesn't matter because you take the ratio between the quadratic and the linear coupling.
So what do you assume anything?
I think you assume the electric yes,
The polarizability or something?
polarizability and yeah, and the size, but then the size we try to measure at the microscope.
Okay, yeah.
Yeah, I mean, absolute is word.
No, I know, but this is I mean, there's lots of different ways to measure mass. It seems like people claim different things as different assumptions. I just was curious what you have to assume in that particular measurement.
No, I'd say polarizability is
Okay, yeah, it's a big
but
one.
not even trivial. So.
Yeah.
But when you measure the size of the particles, those are not the very particles for which you're measuring the
No,
mass in
no.
the trap. This is not like an average measurement.
Yes, but they're quite.
If they are consistent, I'm not criticizing, I'm just trying to make sure.
Can you show you the squeezing plot again?
Yeah.
I was wondering why you chose to do it homodyne and not heterodyne and not homodyne.
Because
You wanted the tomography at all phases, or
yeah, so the heterodyne. So the real reason, I mean, monomotive squeezing has been shown in infinite systems with much better results than this, and it's not particularly interesting if not for being without a cavity, but also that. So the real reason is that we want full optical tomography in order to try and see if we can reconstruct some entanglement between light and mechanics. And for that, so we have a theory paper out in which analyzing perpendicular quadratures of the output light after the interaction, you can infer if you see entanglement between those modes, you can infer there has been entanglement between light and mechanics. So this is the main motivation for which we have taken this intermediate step, let's say. But we expect to see it. There are initial promising results with huge systematic errors that we have to understand through. Also, the code is weird. So yeah, the reason we use, I mean, in principle, so also heterodyne reduces efficiency on the single quadrature by factor 2. So in principle, we will even go lower in squeezing, but that's not the point. I mean, it's never going to be comparable to, you know, better systems.
And question for the size of the particle, how do you decide how big you want to have it? Like, are there advantages if you have bigger particles, or do you only use at the maximum that's reasonable right now? Or?
Good question. So the choice is so going bigger is what in principle we want to do, but it becomes more difficult for a couple of reasons. First, the main reason is that the particle scatters more light, and so having a coherent optical state at those frequencies with all that power is more difficult. You have to get rid of more intensity noise, and it becomes increasingly difficult. So that's the main reason. So if you go to smaller particles, they scatter less, and your shot noise is dominating anyway. And then I think this is the main issue. I mean, of course, if you go to bigger particles, you cannot anymore assume the sub-wavelength scattering, but it will have a different scattering, probably even better for efficiency. And so I would say that reducing noise. So these are the ones that work in the easiest way, and we started there.
I guess I have another question about this on the spread of can you make non-classical states? So once you're in the ground state, could you imagine either like squeezing the motion by either the back action evading measurement or like parametric amplification?
Yeah, this is what we are trying to do next, actually. So we are squeeze mechanical state is still Gaussian, so everything applies.
Yep.
And so we are adding a parametric control by modulating the intensity of the trap in order to squeeze the mechanical motion of our state.
Nice.
Ideally, the goal is eventually one wants to drop the particle, have it evolve in no potential, and if it's even gravitationally interacting, see how gravity is interacting with another ground state particle and something like that. But to do so, you need a very large state, and decoherence is a mess. So the expansion of the state will not be fast enough in general. And so squeezing is a way that one can speed up the expansion of the state spatially, and so yeah, what we're trying to do is to add an optimal parametric control on the intensity of the trap, and then drop the particle.
Okay, there are no more questions, then Lorenzo again.
So there will be lunch outside at 1 roughly, and if you haven't signed on the attendance list, please do so. If you haven't received before, then please have your name and.
Thank you.
Yeah.
Yeah, I will.